Okay, students, welcome to this next session on industrial metallurgy. We are currently discussing the iron carbon systems, and in today's session, I will introduce you to a very important concept in the field of industrial metallurgy. In fact, the most important concept which makes this field so important, and this concept is called the heat treatment processes. So, these are the contents that we'll cover in this session. And very briefly, I would like to tell you that what are the various factors which affect the formation, and also I'll give you a glimpse as to what are the various factors which affect the decomposition of austenite. Okay. Now, the first question comes that why steels are considered as the most important engineering alloys? Why is it that they are the most uh, important commercial materials, or why are they the most commonly used materials in the industry? And there are some very good solid reasons behind that. You see, steels can be produced in abundance very economically, right? So producing steels in a huge quantity has never been an issue. Then the machinability, the weldability, and the response of steel to other major manufacturing processes is very good, which makes its formability into intricate shapes, sizes, etc. very easy. So the machinability, the weldability, and response of steel to other major processes is good. Also, an important characteristic of steel is that the mechanical properties of steels can be improved upon by alloying with varied elements, though this is a costly process. And finally, again, the mechanical properties of steels can be considerably, significantly improved by these processes which are called the heat treatment processes. So you can have the same steel specimen without any change in chemical composition. You can make it very soft and ductile through a specific heat treatment process, and the same steel component with the same chemical composition, if you wish it to be made very high in strength and good in hardness, giving another heat treatment, you can do this. And what is heat treatment? Simple heating, holding, and cooling of the steel. So it's a relatively very simple and cheap process. And steels, and these are a set of various processes. Annealing is there, normalizing is there, hardening is there, and the response of steel to every type of heat treatment is good. You have other elements also which give good response to heat treatment, but then they'll go, like for example, we have aluminum would give very good response to a heat treatment process which is called age hardening, but that's it. If you talk about the other heat treatment processes, aluminum would not respond. But the beauty of steel is that these alloys, when they are given any specific heat treatment for the function that that heat treatment can perform, they'll obey, and they'll bring about a change in their microstructure and properties. And this makes the steel very adaptable, right? So that makes steel very versatile. So because of these reasons, one of the most important engineering alloys that we have, and which are most uh, uh, abundantly used for commercial usage, are steels. Then, having said that, one of the major reasons why steels are so important an engineering material, heat treatment plays a very vital role. So now we begin our discussion as to what are heat treatment processes. Students, heat treatment is a name that is given to several processes which share common steps. Heat treatment, if I define it, heat treatment process is defined as a combination of heating and cooling operations timed and applied to a material system when it is in the solid state, in order to bring about changes in its microstructure and hence in its mechanical properties. So what did I say? Heat treatment is a combination of heating and cooling cycles timed and applied to a materials system when essentially materials system is in the solid state to bring about changes in the microstructure of the material system and hence its mechanical properties. So heat treatment, any heat treatment process is a process which would involve heating of the alloy to some stipulated temperature, which would be called the heat treatment temperature, and subsequently cooling that alloy to the room temperature. And what's the one thing that came in the definition is that you will always remain in the solid state, means you'll never heat the steel or the alloy which is being given heat treatment to a temperature where it comes down to a molten state, right? So you always remain in the solid state and heat and cool, and you heat and cool in such a manner that the microstructure of the material changes. Microstructure of the material changes means its mechanical properties change. So okay, let's see, we'll talk about it in more detail in the times to come. So but there are three essential steps in any heat treatment process. We take the alloy at the room temperature, we heat the alloy to a particular temperature, right? And this temperature is called the heat treatment. Okay, let me share with you that what is the basic principle that is working behind any heat treatment process. Students, the other day we were discussing that the mechanical properties of any alloy system depend upon its microstructure. Microstructure mainly comprises of grain size and the phase details. So heat treatment processes, basically what do? They change the microstructure of a materials system according to the properties that you are desiring in the material system. So every heat treatment process that you would give to a material system, you would give it with a microstructure in mind. So whenever you need some mechanical properties in your material, whenever you need to change the mechanical properties of a material system, the newer properties that you are desiring for in that material system, you must know that which newer microstructure would give me those properties. And then you should know the route, either alloying or heat treatment, through which that microstructure can be obtained, right? So in heat treatment, when we are doing heat treatment for steels, the basic point that has to be understood is that we have to change the microstructure. But then the bigger question is that how do we change the microstructure? The answer to this question is hidden in the fact that where do we get the microstructure that we see at the room temperature conditions in a steel? Minded students, whatsoever phase details you are seeing, see, heating and holding, they decide what type of grain structure is going to come in the steel, and cooling is going to decide that what phase details are going to come in the steel. So what do we do in case of steels is that we know that whatsoever microstructure is being seen at room temperature in the steel has come in the steel because of the austenite transformation. Austenite phase decomposes in a particular manner. Austenite phase present in the steel transforms in a particular manner, and then largely the microstructure that is seen in the steel is formed. For example, when you were talking in terms of the iron cementite diagram, austenite would only transform to perlite. Why? Because you were doing only equilibrium cooling, slow cooling. So one thing is for sure, that whenever you will have a steel with you which is containing austenite in it, if you do slow cooling, austenite will only transform to perlite. But as I said, industry never follows equilibrium cooling. Industry will always follow faster cooling. So you must know that when we do faster cooling of austenite, austenite transforms to what other product phases. But here we are not trying to judge that. Here we are trying to see, we are trying to understand that what does the heat treatment process do for us. So the heat treatment process has this basic understanding that whenever any steel is taken at the room temperature, the first step is to bring austenite structure in the steel's microstructure, and that would come through heating and holding. And then the steel has to be cooled in a particular fashion so that austenite transforms into the phases which we are looking in the final microstructure of the steel, so that we get some desirable properties. So students, the first step in any heat treatment process is heating. Why are we heating the steel? Because we want austenite in the steel, which can be transformed according to our wish. But there is no austenite present in the steel at the room temperature, because austenite is a high temperature phase. So whenever any heat treatment process is given to any steel, the steel from the room temperature is taken to a stipulated high temperature. Right, depending upon whether you need 100% austenitic structure or you need partial austenitic structure. If you are needing 100% austenitic structure, your heat treatment temperature, your temperature to which the steel would be heated in the first step of heat treatment, would be above the upper critical temperature of the steel. And if you need partial austenitic microstructure, and when we discuss heat treatment processes, we'll find out that at times there is a need that we do not need 100% austenitic structure, because for some reasons we'll discuss them. So if you need partial austenitic structure, then you will take the steel to a temperature which is between its lower critical temperature and upper critical temperature. Then students, there is this second step, soaking is generally done. The minor purpose of soaking is that we have to ensure that whatsoever temperature the steel has been taken to, that temperature has been maintained uniformly throughout the cross section of the steel specimen. But this is only a minor reason. The major reason is that whatsoever austenite we have obtained during the first step of heating, that for some reasons which we'll discuss in the sessions to come, is not chemically homogeneous. So when it is not chemically homogeneous, then we do soaking so that enough of diffusion takes place. The diffusion process realizes that there is a composition gradient in the austenite phase that has got formed, and this diffusion step homogenizes the soaking at the high heat treatment temperature, completely homogenizes all the austenite. So now we have this chemically homogeneous stable austenite with us, and we subject it to cooling. And we understand and we know, and we'll also study it in detail in the sessions to come, that when austenite is cooled down at different cooling rates, see slow cooling rate on a temperature time curve, slow cooling rate, fast cooling rate, even faster cooling rate. So depending upon a given type of cooling rate, this austenite will transform into some phases, pearlite, or there are other phases now. For the first time, I'll speak about those phases. Bainite, there is another phase called martensite, right? So we know that which type of cooling rate in which type of steel can give which type of transformation product. So depending upon what final microstructure are we looking for in the steel, we will cool the steel at a particular cooling rate. And after we have brought down the steel to the room temperature, we have obtained a desirable microstructure in the steel, and that desirable microstructure gives us some desirable mechanical properties for which the steel was subjected to a particular heat treatment process. And this all is heat treatment. And we'll now discuss the details of each of these steps in the lectures to come. Fine, students. Then I also wanted to give you some idea as to what are the factors which affect the kinetics of formation of austenite, and also what are the various factors which affect the kinetics of decomposition of austenite. You see, kinetics of formation of austenite depend upon the nature of the pearlite you have taken, the temperature to which the steel is heated, the time for which the steel is held at the heat treatment temperature, the heating rate through which the heat treatment temperature has been obtained, etc., etc. And the decomposition of austenite depends upon the cooling rate that you follow, the nature of austenite that you have. Is the austenite chemically homogeneous? What type of grain size is there in the austenite? Is it fine or is it coarse? It also depends that at what temperature transformation of austenite has started and has ended. It also depends upon the time that you spend at a particular transformation for austenite to transform into a particular transformation product. So these are some of the factors. Now the most important factors which affect the decomposition of austenite are the temperature and the time. And the diagram which explains this effect is called the time temperature transformation diagram. So in the next session, probably I'll discuss that diagram in totality with you. So thank you so much for watching this session. Thanks, students.